This is part 2 of a video series on Riemann sums. So if you haven't watched my previous video, go back and watch that now. Here we solve a problem in which we're given a graph, also a table of values for a function. We're asked to approximate the area of the highlighted region. It's under the graph of f between 8 and 24 using Riemann sums. This problem asks for 3 different types of Riemann sum approximation. In some problems, you might not be given a table of values, just a graph or a formula for the function. If so, your first job will be to generate a table of values, either from the formula or by reading values off of the graph. But first, you'll need to know which x values you need to evaluate the function at. And I'll say more about that in just a second. Let's start with part A. We're looking for a right Riemann sum, which I've shown you here. First, compute delta x. That's the width of the entire interval, 24 minus 8, divided by n, which is 8. And you get delta x is 2. So you have 8 subintervals of width 2. Total width is 16. We need the values of the function at all the points on the x-axis spaced 2 apart from 8 to 24. That is, we need to evaluate the function at 8, 10, 12, 14, 16, 18, 20, 22, 24. I have read off the table of values from the graph for you. If you weren't given a table of values, presumably you can read them off a graph or compute them using a formula, whatever information was given. Now, I don't actually require the graph to answer this problem, but I've shown it here just for pedagogical reasons. Well, some problems might actually ask you, in addition to determining the Riemann sums, to sketch the rectangles on the graph to show that you actually are aware of what you're doing. Now you can see the heights of the rectangles are the function values listed in the second column of my table, all except the first entry, which we don't need yet. So this gives 8 terms, which I'm going to simply add up. Then I'm going to have to multiply by delta x, which is 2. I've taken the liberty of factoring out delta x from the sum, which is a common factor. You can think about the summation notation on the left as well, although the problem didn't ask us to express the sum in summation notation, so you don't really need to write this down unless the problem asks. It's just there for your practice. I have entered the function values taken straight from my table, the second column of the table, and the rest is simple calculator arithmetic. The total area of the rectangles is 218. This is our right Riemann sum with n equals 8. Part B, the left Riemann sum is almost identical, but the heights of the rectangles are the values of the functions at the left endpoints of the subintervals. This time I add all the function values from the table except the last one. Once again, I'm adding 8 values of the function times the common factor, which is delta x, which is 2. I got this expression for the summation notation simply by replacing I by I minus 1 from part A. Here I've entered the actual function values and worked it out using my calculator. The left Riemann sum comes out to 198. Now, for part C, I have asked for the midpoint Riemann sum using n equals 4 subintervals rather than 8 subintervals. The reason is, if you want 8 subintervals of width 2, then you're going to have to evaluate the function at their midpoints, which is 9, 11, 13, 15, 17, 19, 21, 23. Those values were not given in the table. But using the 4 subintervals of width 4, the midpoints of the subintervals, you can see from my graph here, those midpoints are 10, 14, 18, 22. Those are points that are given in our table. And now let's go ahead and work out the Riemann sum. I factored out delta x, which is 4 in this case. Evaluate the function at the 4 midpoints of the subintervals. The notation on the left for the summation I've rewritten in the simplest way I can, but don't worry about that, just to answer our problem. I read off the values of the function from the table, put them in, and add up using a calculator. Now compare. We now have three estimates for our area in this problem: 218, 198, and 212. As expected, these estimates are all reasonably close. Also, as expected, the last one, the midpoint sum, is somewhere in the middle. It's probably closest to the actual area of our three estimates. But without having more data, it's hard to know for sure. So this is what I consider closer to a real-life situation where we're not given a nice formula for the function, only a table of values.